Hello and welcome back to my channel. Today we will be presenting something very interesting and popular as well. Sudoku, Magic Square and SudoMagic. Today it's part 1. Of course we have a part 2, but before that we'll explain in part 1 who are those fellows, Sudoku, Magic Square, SudoMagic, and why they are interesting, what are their characteristic features. And in part 2 actually we'll be solving them by artificial intelligence. Okay. Well, let us start with a funny game. If I ask by showing this number, does it make any sense? Probably your answer will be no, or at best it's a 8-digit number, that's all. Well, then let me split the number in 2 parts, black and green. Then does it make any sense? Probably some of you will answer that okay, the last 4 digits seems to be an year, right? 1887. So if you have guessed like that, then let me give you another clue, another split. 22, 12, 18, 87. Now probably all of you will say, oh, I got it. This is a date. Yes, it is a date of birth. And date of birth of none other than Ramanujan, the great Ramanujan. It's a book written by Parthasarathi Mukhopadhyay in Bengali, which is the translated form, of course, Antohiner Antarjami. I'm coming to the other original books. So let me split further to continue our game. So this is a 3 numbers. Now I am splitting it further to give a 4 numbers series. Okay. Now if you add these 4 numbers, you will get 130. Okay. You can check. Now let me put 4 new numbers in a row A, B, C, D just below the first row, and a couple of more new rows of numbers E, F, G, H in the third row, and I, J, K, L in the fourth. Okay. So why I am going for this direction? If you see that the sum of these 4 numbers is again 139, 139, 139, then isn't that interesting? And isn't even more interesting if you find that the sum of the columns as well is also 139, right? So I think it looks more interesting, and it is much more interesting even if you find that the sum of the diagonals, 2 diagonals, these 2 diagonals again they add up to 139. So what I see, 139 the sum for every row, every column, and 2 diagonals. What about A to L, these 12 digits? Are they really there? Yes. This is for example. The first row is given, and A, B, C, D to L, these are the numbers. And actually this is famous as Ramanujan Magic Square. So you may try with your own date of birth. Actually I have tried with my date of birth, and I could find a magic square having a total, of course, not 39 but 107. This S is unique because this is the sum of my digits in my date of birth. So that is unique, 107. But the remaining 12 numbers that you get as A, B, C, D, etc., they are not unique. You can have more than one solution actually. Why? And then to answer why, you have to wait, see how did he work. Okay. As I mentioned that the original book written in English, The Man Who Knew Infinity, from where Parthasarathi translated into Bengali, and actually this book has been translated in many other languages. Well, so let us focus on Ramanujan's solution. Okay, how we got. It looks like that as if it a sum of two matrices to give the final matrix, and it contains only A, B, C, D in this left hand and P, Q, R, S in the right, and the summation are like this. Okay? As two matrices, and these digits and numbers are actually A plus B, D plus S, C plus Q, right? So you have option to vary with either A, B, C, D. Then P, S, Q are not at your hand because the sum is fixed 22, 12, 18, and 18. Or you can change P, S, Q, R, and then A, B, C, D are not at your hand. So that means you have to choose four numbers arbitrarily. Say A, B, and C, D you are choosing. Then P, S, Q, R are automatic because A plus P is 22. So P is 22 minus A. So if you have chosen A, then P is automatically fixed, and similarly S, Q, and R. Okay. So at your liberty is four numbers A, B, C, D, and naturally you can choose in your own way, differently in different places. So you will get different solutions. Okay. So that is the answer to my why. But you can ask still another question that what is the mathematical rationale or how do he found this solution? That's altogether a separate game. I'm not discussing that. Well, for example, I have shown that the Ramanujan square, the first row remains the same, the date of birth, but the other 12 numbers are different, but still it is Ramanujan square because the magic sum is again 130. So what about the magic sum in general? So let us see for 3 by 3. 3 square number of numbers, right? 1 to 9 for every 3, and the total is 45. But that 45 is divided in 3 rows, right? It's a 3 by 3 case. So 3 rows or 3 columns. So in each row, it should be 1/3 of the total T. That means 45 by 3, that is 15. So the magic sum for 3 by 3 magic square is 15. In general, for n, there are n square number of terms. So the sum of all the 1 through n square number is given by this formula T, and that total T is again divided by n rows because it's a n by n case or n column you can say. So magic sum S is T by n again. And for example, if n is 5, then you will get 65. You can easily check. And if it is 9, then you will get 360 the magic sum. Okay. Now to just show the filling that this is also a square 5 by 5, but it's not a magic square because the column sum or the row sum or the diagonal sum are not same and equal to 65. They're not equal to 65, right? So it's not a magic square. But if you see carefully, this is rearranged 5 by 5 magic square because the magic sum is 65. All rows of columns and diagonals, right? The popular version is of course not 1 through 9 square. That means 1 to 81. Rather, we use 9 sets of 1 through 9. So 1 through 9, similarly another set 1 through 9, and so on, 9 sets. So that is the popular version of the magic square or whatever you say. So you see 1 to 9 in the first row, 1 to 9 in the second row, only rearranged, that is nothing. So to note that 1 to 9 in each row or column or diagonal, but no repetition, right? So in any column you will find 1 through 9. So there must be no repetition along the diagonal and along the row of the set. And the magic sum is, as I have mentioned, that it is 1 to 9. So sum of 1 to 9 is 45. Okay. Now, n can be any number for n by n square, but if n itself is a square number, say 9 or 16 or 25, etc., then something interesting can be added, something interesting more, interesting and interesting more can be added. What is that? Let us see. So here it is again 1 through n square, 9 by 9 case, and naturally the row sum and the column sum are same, 369, but I have marked something by color. Why? Because the inner block, how many? 1, 2, 3, 4, 5, 6, 7, 8. So 9 such inner blocks, or you can call smaller blocks or smaller matrices. Their sum of the elements of this matrix, is also 316. Each of these 9 inner blocks. So we are making it more constrained, right? So if that is happening, then we must say that it is even more, not only row and column, but the inner blocks. And that is possible if the n by n, so n is square, say 9, then we get square root of 9, that is 3 by 3 matrix. If it is 16, n is 16, then we will get 4 by 4, square root of 16, etc. Okay. So what we see that number of sum of elements of row equal to sum of elements of column, and sum of elements of inner block, all are same, 369. But one thing is left. What about the diagonal? Sum of the diagonal elements. Well, we can say that it's going to be too much of constraints. Right? The optimization problem is going to be too constant. How many constraints? If you call it constraint, that that has to be equal to 369, that you can call a constraint. And it is 9 rows, 9 columns, 2 diagonals, and 9 inner blocks. So 29, right? 29 constraints that have to satisfy. Okay. Well, you may not like that much of constraint. So 2 options are there to relax. How? Okay. Firstly, you can think of that. Okay, I will lift 2 constants on 2 diagonals. There is 2 diagonals. I am not asking for 2 diagonals constant. So it is 27 row, column, and inner blocks. Or even more, you can say that okay, let there be 2 diagonals, but I am lifting the constraint on inner blocks, right? So it is 20, much less, 9 plus 9 row, column, and 2 diagonals. So either you keep diagonal and leave the inner blocks, or you keep the inner blocks and leave diagonals. Okay. But then if you are ready to take more challenge, to be satisfied with more constraints, then you can keep both inner blocks and diagonals. Okay, all these 3 problems are actually have different names. The first one is called so-called famous Sudoku. The second one, it's called the magic square. And if you want to keep all the constants, then it's nothing but both Sudoku and magic square. That means combination of these 2, and you can call it Sudoku plus magic square to SudoMagic or MagicSudoku. Right? So the most constant problem. Well, let us have a quick comparative summary. So the common thing is row and column. N number of rows and n number of columns. So 2n number of constants is common. Then for magic square, it is the 2 diagonals more. For Sudoku, it's 9. If it is n is 9, then 9 inner blocks are extra. At Magic Sudoku, both 2 diagonals and blocks. I am considering n equal to 9. Okay. And this 9 by 9, that is 81 elements. Either it can be 1 through n square or 9 square, that is 81, or 9 sets of 1 to 9. It's the popular version. Magic square you can think of any n, but Sudoku and Magic Sudoku you have to take n as a square number, 4, 9, 16, etc. The number of constants, it is 2n as it's common, plus 2 diagonals, so 2n plus 2, and here it is 2n plus 9 inner blocks, so 2n plus n constant, and here the most maximum number of constants, 2n plus n blocks plus 2, that is 3n plus 2. Okay. So naturally we can label as constraint, more constant, and this most constant. Okay. Now let us see quickly that a square of 9 order, a magic square but not a Sudoku. And you see, this is an example where you can check that row, column, and diagonal all are same 45 as expected from the sum, but the inner blocks are not same and they are different. So it's of course a magic square, but not a Sudoku. Now you can think of a Sudoku, but not a magic square. Then you can check that the row, column, and inner block are same, but the diagonals are not same, 40 and 30, not 40. So it's a Sudoku, not a magic square. And in Sudoku, you will see that the diagonals are not 45. So actually, what happens here? Repetition, 1 and 1 is there. Okay. So repetition along the diagonals. But in case of magic square, there is no repetition because all 1 through 9 have to be there. Okay. Now comes the combination, hybrid. That number of, sum of the rows, columns, inner blocks, diagonals, all are equal and equal to 40. Here goes the answer. So you can do a pause and check that yes, it is both Sudoku and magic square. Call it SudoMagic. Okay. Actually, in most of the magazines and daily papers, you will see that Sudoku problem is there, and many people they like it solving Sudoku. But unfortunately, magic square or SudoMagic, they are not here. For example, here I have taken one of the most difficult telegraph Sudoku. Only 25 elements are provided out of 81 spaces. So only 25, and you have to fill in the other. And this is the solution. Of course, this is an AI solution that I will present next video. The questions remain that how to generate, how one can generate this Sudoku problem and how to solve. Of course, usually people try to some extent by reason and then by trial and error. But with the help of computation, you can think of an artificially intelligent algorithm to solve your problem. So for that, you have to wait for Sudoku, Magic Square, and SudoMagic Part 2 video of the series, where we will be solving these problems by an artificial intelligent method called simulated annealing method. Until then, thanks for watching. Thank you.